Okay, great. So let's start today seminar, and we're happy to have Ilya Dumanski from MIT, yeah, who will speak about a quantum loop group, from quantum loop group to coherent Satake via fusion product. So Ilya, please.
Thank you very much for the invitation. I'm happy to speak at this seminar. I'll start with defining a purely algebraic, rather elementary notion of Feigin-Loktev fusion product of modules over currently algebra. And then I'll try to explain how it helps to study coherent Satake category by relating to the category of modules over quantum loop group. So let's start. For this notion of Feigin-Loktev fusion product, we have G, a simple Lie algebra over complex numbers, and we consider its current Lie algebra. So it's just we tensor it with the polynomials in one variable. Okay. We consider modules over this Lie algebra with the following properties. Let's consider two of such modules. They will be cyclic. So when I say cyclic, I mean that they are generated over the universal enveloping by a single vector called cyclic vector. Okay. Graded.
No, one thing is that you are writing something, but we do not see it on the screen. At least I do not see it on the screen. We can follow your notes, but am I alone or other people also do not see anything on, I mean, any writing on the screen? Your device is probably not connected. I don't know.
From my another device, from my laptop, I think I see what I write.
Okay, let me ask other people.
Yeah.
So I don't know.
I can say graded.
Yes, graded is the last word I wrote. That's right.
Okay. Strangely enough, it's something probably I have no idea. Anyway, so I do not see any writing on the screen. But go ahead anyway. I will follow your notes.
Okay, sorry. Yeah, but please let me know if
it's no, I don't know. It's problem probably with my settings. Go ahead.
Okay, yeah. So they're graded. So what I mean by graded is just that this Lie algebra is naturally graded by degrees of t. So the degree of an element t x t I is equal to y, and this module should respect this grading on this Lie algebra. Graded finite-dimensional g of t modules. And I can twist them a little bit. By that, I mean that I can take two numbers, just complex numbers, and we can define mi of ci to be a new module over g of t in the following way. So as a vector space, nothing changes. It's just mi, and xt powered I acts, or let me use another letter, xt powered k acts as xt plus ci powered k. So I just have an automorphism of the polynomial ring. T goes to t plus ci, and I compose this automorphism with the action on mi. Okay. Great. Now, an easy fact. If C1 is not equal to C2, then the tensor product M1 of C1 times M2 of C2 is again cyclic. So note that if I take tensor product of two cyclic modules, in principle, there is no reason for it to be cyclic, but if I twist them on distinct numbers, then it's like a Chinese remainder theorem type result or Vandermonde determinant type result. It is non-zero. So in this case, this tensor product will be cyclic. Great. So note that it is cyclic, but no longer graded, because this operation obviously doesn't preserve the grading. So instead of grading, I can define the filtration on this tensor product space. And the nth term of the filtration is just the nth part of filtration of my universal enveloping applied to this cyclic vector. So note that I fixed cyclic vectors, and this grading does depend on my choice. Okay, so just to be clear, by this filtration on the universal enveloping, I mean filtration which comes from grading by this t degrees. So it's not PBW filtration or something like that. It is filtration coming from grading by polynomial degrees. Great. So now definition, Feigin-Loktev fusion product is, we will denote it M1 asterisk M2, is the associated graded with respect to this filtration of this tensor product. So this is naturally a GFT module. Which now has all the properties which M1 and M2 had. It is cyclic, now graded. We took the associated graded, and obviously finite dimensional.
Ilya, I have a question. I mean,
yes.
How general this construct is? It specific to the enveloping algebras? Because what you use basically the graded algebra, cyclic modules, and
Right, but
strange fact that the tensor product of two cyclics is cyclic, but still, is it an algebraic construction or it's very special?
So I need an automorphism of this universal enveloping which maps T to T plus C, which is, I mean, I'm not sure if there are other.
No, I'm not sure. No, I mean, you needed to define this evaluation modules, that's correct. But forget about this C1 and C2.
Yeah.
If you have just two cyclic modules, I mean, some of the graded algebra with the properties that, and so you try to define this fusion, whatever, Feigin-Loktev type product taking associated graded for the tensor product of the two. What will not work? Why you will not get a monoidal structure?
Oh, those two modules, MC1, those are not graded. They are only filtered.
Yeah, but the algebra is graded. Actually, I'm not sure that you need even grading on the algebra. Maybe some filter. I don't know, like algebra of differential operators on.
But again, in the definition, I really need this automorphism, which, so I take these two twists to automorphism, take tensor product, then take the associated graded. So I'm not sure what's this one dimensional
but your I'm confused. Your conjecture says, actually not yours, but Feigin-Loktev says that it doesn't depend on C1 and C2. So you can just put C1 equal C2 equal whatever, 0 or 1.
No, if they are
different, 0 and 1. One is equal to 0, another equal to 1.
Yes.
So, okay, then you do not have this C1 and C2, so you do not have this automorphism. So then
No, but if C1 equals 0 and C2 equals 1, then I need to apply this automorphism to this module, then take tensor product. And then,
okay. So, but besides
I mean, in
of the
principle,
automorphism,
beside of the automorphism, it's rather general, yes, but
okay. So you have just C star action on your own.
yeah, something like that.
Yeah.
And,
Okay. Okay. Thank you.
yes, right. And oops, sorry. Yeah, and so the conjecture, which Jan mentioned. So yeah, you can note that C1 and C2, in principle, this construction depends on the choice of C1 and C2, but it's the conjecture still not proved in general for arbitrary M1 and M2 that in fact this module does not depend on C1 and C2 while they are non-equal. Otherwise, this is not well defined. Okay, so maybe the main.
Do you expect the associated graded edge module still cyclic?
Yes, it is still cyclic. Yes, it is an exercise that if this was
The
cyclic,
filtered is cyclic, the associated graded is cyclic.
yes. Thank you. Yeah, let me write this cyclic. Okay. So the main maybe point of my talk that this notion helps to study the following two categories. So I have a monoidal category of finite-dimensional modules over a quantum loop group with operation of tensor product. And on the other hand, I have coherent Satake category, which I will define in a second. It is a category of G-ovoid covariant perverse coherent sheaves on the affine Grassmanian with operation of convolution, which I'll also describe. And here we have this category of G of T modules with all these properties, cyclic, graded, finite dimensional, and this operation, which we don't know if it defines a monoidal structure, we don't know it is well defined, so but still we have some kind of category. And we have some kind of relation from this category to this, which I will also explain, but this is called graded limit. It is a variant of classical limit, just letting q equals 1. I'll explain in detail. So it's not a functor, but for some modules here, it produces modules here, and these operations are intertwined. And we also have some relation here, which will be just taking the derived global sections, and in fact, dual derived global sections, which also in general is not a monoidal functor or anything, but for some modules here, it produces good modules here, which, and again, these operations are intertwined, and this helps to study this category using this category, because this geometric category is much less studied as opposed to this algebraic category, and some results, I'll explain it further, are known for this category, and one can translate them to this category by this procedure. Okay, so
may I ask you, because you kind of this after all, this Feigin-Loktev fusion product, does it define a monoidal structure or it's not? I'm confused. The very bottom category, is it monoidal?
So it's not known that this operation does not depend on parameters in general, but if you assume that, then it should define a monoidal structure, yes.
Yeah, because there is a more general notion of, like meromorphic monoidal, meromorphic tensor category, and so then you can still keep parameters. Okay.
Yeah.
But the other categories, they are fine, and Q is general for
Q is not the
equivalent.
root of unity, yes.
Okay. And if we assume that this Feigin-Loktev gives a monoidal structure, so these two maps, do they expect to be monoidal functor or they don't?
No, I don't think so. So it's really some tight relation. For example, if you take arbitrarily perverse coherent sheaf here and take derived global sections, you don't get cyclic graded modules. You get some complex element of derived category of such things, which are not cyclic in principle. And so maybe there should be some substitution, some generalization of this
But
Feigin-Loktev.
this GT mod, do you mean all finite dimensional, just cyclic? Because it's confusing.
So this operation is not
No,
defined.
it's defined. Yeah,
Yes.
but when you go down, this the bottom category, you don't say that. Maybe
Yeah.
it extends. I don't know.
Yeah, so that's a good question. I also don't know if it extends. Maybe there should be some substitution, but yes, here I mean all these properties cyclic, graded, finite dimensional.
Okay. So these are just maps, and so you have two sides of the triangle. Is it a third one?
It's also a very good question. I think these categories are somehow related, but I don't know any better relation than the one I'm going to present.
Okay.
Yes.
Okay.
For example, one thing which is common for them is that they have cluster structures or something like that, which is also which I'll also say about a few words. Okay. Great. So let me now speak about this category. It is a category of some sheaves on the affine Grassmanian. So let me define it. It's called coherent Satake category. So for this, I need to take algebraic group of a joint type with the algebra equals to my G taken above. And we consider the affine Grassmanian, which is defined as certain in scheme. We can shortly write it as G of K mod G of O. Here K is the field of Laurent series. O is the ring of Taylor series in one variable. And this in scheme, it has a certain line bundle. Its Picard group is Z, at least Picard group of each connected component is Z, and there is a very ample generator of this Picard group, which I'll denote by L, and it's called determinant line bundle. Also, my current group G of O acts by multiplication from the left on this affine Grassmanian, and orbits of this section are in natural bijection with dominant co-weights of G. And for a dominant co-weight lambda, I denote the corresponding orbit by Gr lambda check. It's called a affine Schubert cell. Okay, so now I want to define certain category of sheaves on this in the in scheme Gr. And let me say that the motivation for considering such category initially came from a more standard notion, of usual perverse sheaves, geo-equivariant perverse sheaves on the constructible perverse sheaves on the affine Grassmanian. So let me say that it is, by very definition, a certain abelian subcategory inside the derived category of constructible sheaves on the affine Grassmanian, geo-equivariant. And it's called Satake category because it's the main object of geometric Satake equivalence. Satake category. And yeah, let me say that geometric Satake equivalence tells that this category is equivalent to the category of representations of a Langlands dual group, but we will not consider it. Instead, we will consider its coherent analog, which we call P G of O on group. And it, by definition, this will be also an abelian subcategory now inside the derived category of coherent geo-equivariant sheaves on the affine Grassmanian. And let me define it. Okay, so F, an element of this derived category of coherent sheaves. Is perverse if for any orbit let me denote by I lambda check the inclusion of the generic point of this cell. And the following two conditions should hold. This is thing parallel to constructible case, and this, yeah, so star pullback of F should lie below certain degrees, which is 1/2 of dimension of GRU lambda check of modules over the local ring of this point. And second, somewhat dual condition is that, sorry, this was Schrick pullback, this is star pullback of F should lie above the same degrees.
So maybe, I don't know, graduate students, before you define perverse, it's a question how you understand DB Koch, well, equivariant on the int scheme.
Right. So yeah. Let me say it. So these Schubert cells are finite dimensional, and affine Grassmanian can be thought and should be thought as an inductive limit of. Let me write it. Inductive limit of these Schubert varieties, the closures of Schubert cells. And when I talk about coherent sheaf, I mean that it is supported on some finite dimensional piece. So yeah, this category of coherent sheaves or derived category of coherent sheaf is just limit of these categories. Each object lives on some finite dimensional part.
Mm-hmm.
So it should be some sort of, like, we think of it as like some sort of diagram sitting over the diagram of the limit diagram of the Schubert cell.
Right. Yeah. So, but starting from after some finite. So yeah, for example, you take this sheaf on some Schubert cells. So if you now have this embedded to some other cell, then yeah, so you think about this just as sitting here. Yeah, I mean, probably that's what you said, yeah.
Okay. And then maybe one other question is, when I think of perverse sheaves, I think of stratification. Here we're sort of thinking roughly, is the stratification coming from the orbits of the group action?
Exactly, yes.
Okay.
Exactly, yes.
Okay, great. Thank you.
Yes, thank you for your questions. Right, so let me say that if you see this for the first time, that may seem as a weird definition, but yeah, in fact, so this definition for coherent category comes from the same actual definition, but for constructible sheaves as opposed to coherent. And there it is, for example, yeah, there is a Riemann-Hilbert correspondence which relates this category of perverse sheaves to the category of D modules. So it's a reasonable thing, but yeah, you can think about these perverse sheaves just as elements of derived category, which some conditions on sitting above and below certain degrees when restricted to these G orbits. Okay. Yeah, so now the fact. So also let me also say that unlike constructible case, constructible perverse sheaves are well defined for any stratification. Here it's more subtle, so you cannot take arbitrary stratification of arbitrary variety and define this T structure there. But in this case, in the case of Grassmanian and stratification by G orbits, it's fine. But yeah, we will not go into these details. Yeah, so this category of perverse coherent sheaves is abelian, Artinian, which differs it from usually abelian category of coherent sheaves, monoidal category, let me give an example of an object in this category. So important example for us, P lambda L is, I take the determinant line bundle, which I mentioned, take its Lth power and restrict it to this finite dimensional part, and also do the cohomological shift on this very degree, which appears in the definition. Yeah, oh yeah. So, or maybe more formally speaking, I multiply this line bundle by the structure sheaf on this Schubert variety. So let me say that if you are more familiar with constructible case of perverse sheaves, there you can take local systems and put it in this degree, and they will be perverse. Here it's the same, but instead of local systems, you have line bundles, or more generally vector bundles. Okay. Great. So now let me say a few words about this word monoidal here. Where does monoidal structure come on this category? So one can form a morphism G of K over G of O times Grassmanian to Grassmanian, which maps point G X to G applied to X. So obviously factors through this quotient here. It's called the convolution morphism, and given Fg in this category, or this works also for elements of derived category as well, but this operation preserves perversity. Yeah, so we defined F star G, this monoidal operation here, to be the derived push forward of the so-called twisted product. So yeah, given f and g, one can naturally form a sheaf on this space and take its push forward with respect to this map. And one can show that this still is perverse. Okay, so this is just a few words about this monoidal structure. Great, and let me now state the main conjecture about this category. This is a conjecture by Cautis and Williams. Which is also their theorem in type A, or more specifically, G equals GLN. Let me state this conjecture for simple lace types, just for it to be easier. In fact, it is expected with a slight variation for in arbitrary type. But yeah, the conjecture is that this category is a monoidal cluster categorification let me write it just for sake of completeness with this matrix. But so if you're not familiar with the cluster categorifications or cluster algebras at all, I will not speak about that in detail, so I will not need it in the rest of the talk. Here sees the Cartan matrix. But yeah, I just wanted to emphasize the motivation for what will follow. Yeah, and
Cartan matrix of what in the case of GLN?
In the case of GLN, you need to add an extra frozen vertex to this cluster algebra because you kind of have this extra torus. But yeah, for G being a joint type for simple, it is stated like this. So yeah, I assume G is simple of type AD. For GLN, you have some extra. You should have some extra data. But for SLN, it should be like this, as written here.
Yeah, so basically you take the quiver, AD Dinkin quiver, you make an affine Grassmanian and construct this category, and so that's a K-Grassmandic group of this monoidal category is a cluster algebra corresponding to this quiver. That's
yes, exactly.
Yeah. Okay.
But yeah, I mean, it's a part of the conjecture. What you stated about K-theory is part of what is called monoidal categorification. You also expect the objects in this category to behave like cluster variables in the cluster algebra. So it's a categorification of what you said. But what you said is a part of this. Yes.
Yeah, you mean there is a distinguished class of probably simple objects, which correspond to cluster variables.
Mm-hmm. And when you perform mutations at the level of cluster algebra, you get new objects, and these mutations should come from short exact triples in this category. And getting a new cluster variable, you should get a new object category.
So the number of cluster variables in each cluster is twice of the rank of the group.
Yes.
So those, for example, initial cluster variables, do you have specific representations in this category?
Yes, great question. Thank you. They are actually expected to be P omega I check 0 and P omega I check 1 in these notations here. So it's 0th power of fundamental Schubert varieties and first power of, so yeah, just structure sheaves of fundamental Schubert varieties and determinant line bundle restricted to these fundamental Schubert varieties. You have two R objects, and they're expected to be in the initial cluster. Yes. Okay. Yeah.
And just, I don't know, it's rather a philosophical question. Is there any motivation, any reason why this should be so?
Yeah. So
normally people consider some much simpler categories, like indeed finite-dimensional representations, UQ of G, and this kind of stuff.
Yeah. So about this maybe is my next remark, and I think historically that's how this cluster structure was invented. Is that in fact this is a particular case for a pure gauge theory. Of what's expected for other K-theoretical Coulomb branches.
So this is an example of this BFN space with trivial representation of what?
Exactly. Yes.
Yeah. Okay.
Yes. So historically, I think it was conjectured by Gayotta. Well, maybe not conjectured, but expected. I don't think there was a precise conjecture that K-theoretical Coulomb branches should have cluster structure. And Cautis and Williams somehow categorified this expectation. They defined this category actually for any BFN space, but for the space of with trivial matter, this category is just the category of perverse coherent sheaves, which was defined before them. And this has a physical meaning, which I cannot say much about, but it should be some category of line defects in this gauge theory. And this is it's also expected to have cluster structure.
And for non-trivial representations, in this,
I think so. At the level of K groups, at the level of just Coulomb branches, there is a paper of Alexander Shapiro and Gus Schreier, who constructed an injection. So they have some relation for K-theoretical Coulomb branches of queer gauge theories with the cluster algebras. But at categorified level, I think nothing is done.
Yeah, there is also, you see this 4D and equal to theories, they come from different sources, and there is this class S theories, which are much more closely related to cluster algebras because of this Fock and Goncharov story. And I think there was a paper by Allegretti with somebody. They try to compare. I recall that in their story, the representation is not trivial. That's why I'm saying you. Okay, there might be also examples, maybe not that general, but which comes from triangulation of Riemann surfaces, but I'm not sure how it is related to affine Grassmanians. I have no idea. Okay. Yeah, all right, thank you.
Okay, yeah, so once again, if you don't know anything about Coulomb branches or cluster categorifications, I will not use this notion in what follows. So what I want to say is one step of proving this conjecture. One first step is so, as I said, it's not just an isomorphism of K group of this category, but it's also some categorical properties, in particular that these cluster mutations should come from a short exact sequences in this category. And yes, to prove that this one actually need to construct some short exact sequences, and this what I will explain. The theorem is that there are short exact sequences in this category. So I use the notation PIL equals P omega I check L. Let me write them and then I'll comment. So yeah, I use the notation J tilde I if I and J are connected in Dynkin diagram I. And here I is an element of Dynkin diagram and L is any integer. So okay, it's what's written here is some short exact sequence of sheaves of this form and their products. And let me say that again, if you don't know much about cluster categorifications, then just keep in mind that this is not some just arbitrary short exact sequence. It's an important one from point of view of this conjecture. And if you are familiar with cluster categorifications, then let me say that since these objects are expected to be the initial cluster, then what's written here is precisely the one-step mutations. If you mutate at, say, this object for L equals 0, then maybe for L equals 0, we rather mutate this object, and we get kind of this. So in Grothendieck ring, this short exact sequence yields a cluster relation, and this theorem tells that it actually comes from it is of categorical nature, this cluster relation. Okay, great. So let me now say
because this short exact sequence gives the mutation, as you said, right?
Yes.
So the kernel part is the initial seed. So, for example, and where is the cluster variable? Can I read the cluster variable for the mutate seed?
Yeah. So, for example, let L equals 0.
Mm-hmm.
Then this is precisely in the Grothendieck ring. This sequence yields you precisely the relation which you expect if you mutate at this cluster variable with respect to this cluster matrix.
I see. So the cluster matrix has two. I mean, here the i's are the number of corresponding to the rank, and the l's corresponding to the you're starting from 0. That's assuming that's the initial set.
Yeah. Mm-hmm.
And you have two such in the middle you're doing the tensor product of those.
Yes. So this will be a new cluster variable. How it's called if you have mutated
I
xi,
see. Okay.
you get xi prime. This is what you get.
The product equals the sum of the products.
Yes. Product equals to sum of products. Yes. And here you can see that, like in Cartan matrix, there is one negative in each row. There is one one positive entry, which is 2 at the diagonal, and this is precisely stands for this monomial, and also a few negative entries, which are precisely these ones. Yeah. Did I answer your question?
Oh, yes, it did.
Thank you. Great. So now how we will prove this theorem. And here comes this diagram, which I wrote in the beginning about relation to quantum loop group. So basically the strategy is the following. We have some short exact sequences in this category of modules over quantum loop groups, which are called Q systems, and they are pretty well studied. And then we somehow go to this category, get short exact sequences here for this Feigin-Loktev fusion product, and then we somehow are able to lift them to this coherent Satake category. So let me now explain this arrow in the initial diagram from coherent Satake category to G of T modules with Feigin-Loktev fusion product. So the precise statement which I meant by that arrow is the following. So if L1 is greater than or equal to L2, then the following holds. Great. So yeah, up to this holds up to cohomological shifts, because as I explained, these objects are supported actually in some non-zero cohomological degree, and you somehow need to put them in the same degree. So, but let's don't care about that. Yeah, then so when I write R gamma, what I also mean that in fact all these shifts are concentrated in a single cohomological degree, and the convolution operation of shifts here is intertwined by this functor of dualized global sections with this Feigin-Loktev fusion product. Great. So let me give an idea of the proof of this theorem. Just to let you feel from like what on the geometric side stands for these say constants involved in the definition of Feigin-Loktev fusion product. So sketch. Let me just say that there exists the so-called Beilinson-Drinfeld convolution diagram. So yeah, let me say phi is the projection from G of K to the Grassmanian, and I define convolution. I wrote previously convolution of infinite-dimensional Grassmanians. Now I need a finite-dimensional piece of this. Yeah. It's just, yeah, you take finite truncations of that space. And yeah, since all coherent shifts are supported on some finite part, you can like always take such thing. Yeah, and so claim is that there exists the certain scheme, which I denote gr lambda mu A2, which lives over A2, and there also is a line bundle depending on L1 and L2. So this can be called Beilinson-Drinfeld, let me say BD, convolution diagram. That's a variant of Beilinson-Drinfeld Grassmanian.
So A2 is a space of pairs C1 and C2
Exactly. Yes, yes. So yes, you should think about this constant involved in Feigin-Loktev fusion product as space of these things. Yes, and so let me just explain which properties this space has. Has the following properties. So over a point away of the diagonal, the fiber of pi is just the product of these Schubert varieties, and the fiber of this line bundle L1, L2 is just the exterior exterior product of powers of these determinant line bundles on these spaces. But now if I take a point on the diagonal, phi inverse of, well, 0, or let me rather say C, then we get nothing else but this convolution space. And when I restrict this line bundle, what I get is precisely this twisted product of the same line bundles. And let me say that if you take sections of this line bundle on this space, and you take them a fiber of these sections over this non-diagonal point, what you get is just tensor product of sections here, right? So it's just a tensor product. But when you somehow tend to 0 point, what you get at the level of sheaves, you get convolution of these sheaves, of these line bundles. When you take the global sections, this is precisely these global sections of convolution. But algebraically, you somehow tend these constants to 0, and this precisely is intuitively what Feigin-Loktev construction is about. You tend this constant involved in the definition, tend them to 0, which formally speaking means that you take the associated graded. But so at the level of section, this will give you this isomorphism. So this is a very rough sketch, very intuitive, but I just wanted to explain which geometric structure stands behind this relation to Feigin-Loktev fusion product, and it is this Abelian-Sandrinzel deformation over A2, which, yes, should be thought as this space of constants C1, C2. Okay. Great. So now let me move to quantum group. I will be very brief here, but I will explain now how we can use this quantum loop group to extract required exact sequences. So that arrow in the diagram which I wrote in the beginning was graded limit. Here it was derived global sections, and I explained this connection. For this arrow, let me briefly explain what is the graded limit. It was developed by Chari and collaborators. So if you take a module, finite dimensional modules over UQ hat, you can tend Q to 1, and so in general, what you get will be a module over G of T inverse, so the loop algebra of G. But sometimes it is actually a module over this algebra quotient by T minus 1 powered n for some large n. So this ideal large power of t minus 1 will act by 0 in this module mq tends equal to 1. And let us rewrite that. Yeah, so it's just elementary algebra. T will be, let me write that properly. It's G tensor C of this algebra. Yeah, and so one can note that T will be already invertible in this quotient. So we don't actually need to add T inverse. And then we can just map T to T minus 1 or maybe T plus 1 to get just T times C of T by T powered n. That's why it's called graded limit. We somehow make this twist to make the module graded. So, and this allows us to consider it as a module over our loop algebra G of T with a large power of T acting by 0, which you will have anyway if you have a graded finite dimensional module. So it's not surprising. Yes, and it is a, let me also add that it is a graded module over this algebra. And the general expectation here, which is proved for a number of modules over quantum loop group, is that this operation of graded limit intertwines tensor product with a Feigin-Loktev fusion product. Yeah, let us denote M log graded limit of M. Yeah, it's G of T module. So yeah, particularly modules which will be important for us, which I will not define, but I will say all the properties which we need from them are Kirillov-Reshetikhin modules, KRIL, Kirillov-Reshetikhin. So again, I will not give the definition here. I is an element of Dynkin diagram. L is integer. For experts, there also should be a spectral parameter for full generality, but I will not care about it, so I omit it in the definition. But yeah, what is important for us is that it's a theorem of Naoi. Is that precisely that relation which I mentioned to be expected? It is proved in this case, namely, if I take tensor product of two Kirillov-Reshetikhin modules and take its graded limit, it's nothing else but the Feigin-Loktev fusion product of graded limits of Kirillov-Reshetikhin modules. One.
And Kirillov-Reshetikhin are the simple objects.
Yes. 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 So the definition of them is just they are modules with some particular Greenfield polynomial, natural one. But yeah, again, maybe let's not go to that. Yes, and now the key property which we use is that, in fact, these are G of T modules, and in fact, graded limit of I Kirillov-Reshetikhin module is just isomorphic as a G of T module to these global sections of this simple perverse coherent sheaf with the same data. So it's supported on ith fundamental, Schubert variety, and lth power of the determinant line bundle. So yes, and this is how this, what I meant by this diagram in the beginning of my talk, that there are modules here, Kirillov-Reshetykhin modules, such that their graded limit is the same as the graded limit of some certain good sheaves here. And this somehow helps to translate facts about these Kirillov-Reshetykhin modules to this coherent Satake category, which is good because these Kirillov-Reshetykhin modules are just for them. There is no. It is known that there is a short exact sequence of this type. It's called Q system. And now let me let me say that here I actually used that I'm in type ADE. So I said in the beginning when I stated this categorification problem that I am in ADE type, and well, actually what I said before was true for any type, but here I used that I'm in simply lace type. In arbitrary type, I'll have a little bit different. Okay, but now let me sketch the proof. This theorem about cluster quantification, or sorry, about short exact sequences. It was theorem 1, I think. And in fact, in this category of UQG hat modules, and we have short exact sequences, which are called Q systems. I think in arbitrary type, they were constructed by David Hernandez. And yeah, let me say that they stand for cluster categorification of certain subcategories inside this category. They are of this form. And now the strategy of the proof is that first we take graded limit and show that the graded limit of this short exact sequence is still a short exact sequence, which is non-obvious because it's not a functor in general. If you take let q equals 1, a priori there is no reason for it to be again short exact sequence, but in this case it actually is. And actually this part was done by Chari and Venkatesh. Great. And now how to, so we have this short exact sequence in the category of G of T modules with the Feigin-Loktev fusion product. How we leave them to coherent Satake category? We just use the very standard SER correspondence or whatever, which describes coherent sheaves on projective varieties as modules over the homogeneous, graded modules over the homogeneous coordinate ring. It turns out to be useful here. So, yeah, sheaf F supported on some lambda check is the same as graded module gamma of F times Lth power of this line bundle. And yeah, it turns out that each graded component is this graded limit. Each graded component of the short exact sequence which we want to construct of a Q system. So for various L here appear, but I is fixed. Great, and that's the idea that helps you to construct this short exact sequence here. Let me at last mention that, in fact, this Q system on quantum loop group, it is a little bit different from what we construct here. Namely, these two terms are somehow interchanged. So here they are, in this order, and there their analogs are interchanged. And that's because in the course of the proof, at some point, we need to do a homological shift and construct a distinguished triangle in the derived category with it naturally appears with the homological shift of these guys, and so it somehow yields precisely what it was expected in this case. Okay, I'd like to stop here. Thank you very much.
Thank you. Yeah, it's kind of a bit strange that this UQ of G is already UQ of G hat modules. It's already a monoidal category. Yeah. So, and it is known that it was used for categorifications of cluster. Okay, so then why people do not try, maybe they did, to connect directly UQ of G hat modules with this Cautis and Williams category?
I don't know. So what I can say is it looks to me that you kill the spectral parameter when you go to this category of Cautis and Williams, or actually this category was originally considered by Bezrukavnikov, Finkelberg, and Mirkovich. But yeah, the idea of cluster structure is due to Cautis and Williams. Yeah, so I don't know. That's a very good question. If there is a more precise, more direct relation between these categories, but yeah, for now that's the strongest precise statement about relation is the one I stated.
Also, as far as I remember, this Cautis and Williams, they have kind of meromorphic braiding on their category, which is also true for UQ of G hat, but I'm not sure about this Feigin-Loktev. So yeah, it's a bit strange. Yeah, all right. And also, if I remember correctly, this perverse, this Cautis and Williams category, it's somehow related to the category of representations of the affine Yangian or something like that. Is it true?
Affine Yangian.
Yeah.
Well, that would be interesting for me, but I don't know anything like that.
Okay.
Well, so sorry, maybe there is a recent paper. Unfortunately, I don't remember the authors, but they defined like the Yangian of like tangent Lie algebra.
Yeah. Abedin and New. Yeah.
Yeah, that's right. Yeah, so they define it for what is called a perturbative sector. So you take not the whole affine Grassmanian, but you take its open part, which is just you take like G1 of T inverse applied to this thing, which is an open part of the affine Grassmanian. And so it is not G of O equivariant anymore. And I am not sure how to define this T structure. There is no natural. So I don't know how to relate this, but yeah.
Okay. All right. More questions?
So in that mutation case, have been thinking of the special case, for example, in SL2. So in this case, the taking Kirillov modules probably is more familiar to our students. So can you explain in this case what that means? For SL2, there is only one simple roots.
Yeah. So for Kirillov reciprocating modules of
Let's go to the category earlier you were doing this cluster categorification.
Yeah, so then P omega 0, so the affine Grassmanian for SL2, or rather PSL2, it has co-weights are parameterized by dominant co-weights are parameterized by non-negative numbers, and the dimension of this n omega is just n, and for example, for this case,
so
we get
your N is running starting from 0, right?
Sorry?
Your N is running starting from 0. So
yes, that's right. That's right.
There are different ways of parameterizing Haskell weights.
Yeah, from 0, yes. Zero-dimensional part is just a point. Then one-dimensional is just P1. And on P1, you have line bundles parameterized by L just by integers. And that's precisely Lth power of the determinant line bundle restricted to this. Yeah, sorry, that's a closure actually. So you have these line bundles on P1, and they are precisely what is there, what is happening there. Yeah, but then if you take 2 omega, then this will be some surface which is not smooth anymore. So it actually is. I think about this as you take P1 vibration on Pi1, and then you construct one horizontal P1. So it's some, I don't know, some can imagine is like something like this, some surface. Yeah. So I don't know. This point here is 0. And the open part is Schubert cell. Yeah, I mean.
Yeah, the mutation formula short exact sequence looks in SL2 case very close to the. The
mutation. Oh, right. Yeah, sorry. Then let's write it here. Right. So then what you get is P1 P11 times P sorry.
Because there is only one single.
Right. Here you have you have empty product, right? So yeah, there will be one.
There is only one copy of that, but on the receiving on the right hand side there will be a tensor product of the same thing.
Yeah, that's right.
I see. Thank you. Yeah, that helps.
Oh yeah, sure.
Okay. More questions? Well, if there are no more questions, then this is it. So thank you, Ilya.
Thank you very much for the invitation.
Yeah, and this is it for today.
Thank you. Bye.